Okay, what we're going to do today is we're going to do the 5.2 notes, trigonometric ratios in right triangles. So first we have to establish what exactly is a right triangle, and that's any triangle that has a right angle in it. As you can see, the bottom right angle right here, I'm highlighting in blue, is the right angle. Once we've established that, then we can talk about the sides of the right triangle. In the right triangle, we will establish one of the angles other than the right angle as an angle we could call it A or B, but in most cases, we usually label it as theta. You can see that little symbol down here, theta. So when you talk about the sides of a right triangle, you're going to talk about them with regards to one of the angles. So with regards to theta, if we would label the side that is opposite of theta, well, we would label with the label opposite. It is the opposite side, so we call it the opposites. Quite obvious. The second is what's called the hypotenuse. The hypotenuse is the longest side in the right triangle, which is always the one opposite of the right angle. So the hypotenuse would be over here. And the side that's left is the adjacent side. So that side is adjacent to theta. Once we've established what the side names are, then we can talk about trigonometric ratios. There are three different trigonometric ratios. There's sine of theta, cosine of theta, and tangent of theta. Those are the three basic trig ratios. There are other trig ratios built off of these three, but these are the three basic and main ratios. Now, those ratios have the abbreviation of SIN for sine, COS for cosine, and TAN for tangent. And it's always of an angle. In this case, we're speaking about theta. So trigonometric ratios are exactly as you would think. They are ratios of something, and specifically they are ratios of sides. So sine of an angle talks about the opposite side in a ratio against the hypotenuse. So sine is the ratio of the opposite side over the hypotenuse side. Cosine is the adjacent over the hypotenuse. So the length of the adjacent side divided by the length of the hypotenuse would be the cosine of an angle. And tangent is opposite over adjacent. Now there's a little phrase that you may have heard before. It's called SOHCAHTOA, spelled SOHCAHTOA. SOHCAHTOA stands for the three trig ratios: sine, opposite over hypotenuse, SOH, cosine, adjacent over hypotenuse, and tangents, opposite over adjacent. It's just a little simple phrase to remember what the ratios of the sides are. Okay, now that we've established what they are, we can put them into action. So here you can see we have an example, and the example asks us to find the values of the sine, cosine, and tangent for angle B. So everything's going to be based on angle B. So we should label the sides according to angle B. So the side opposite of angle B, we're going to speak about as the opposite. The side that is across from the 90, the longest side, is the hypotenuse. And the side that is left, referred to as the adjacent side. We also can label these sides in terms of letters A, B, and C. Now the angles are usually labeled with capital letters. As you can see, we have capital A, capital B, and capital C. The sides opposite of those angles are the little letters of those. So the opposite side, we'd also could say is side B. So we could say as little b. The hypotenuse we could call little c, and the adjacent side we could refer to as little a. So when we're talking about side A, side B, and side C, we often refer to them with little a, little b, and little c. Now, that's helpful because in order to find the third side, we have to use what's called the Pythagorean theorem. Now, the Pythagorean theorem you should have seen in geometry, and that's a squared plus b squared equals c squared. And those are referring to the three sides. So if we replace what we know of these, side A we don't know, so that's a squared. B is 18, so that's 18 squared. And C is 33, so 33 squared. Okay, and again, the reason why we're doing this is because in order to talk about sine, cosine, and tangent, okay, and talk about what those would be for angle B, we would want to know the three sides. You must know all three sides before you can actually talk about the ratios. So we have to find this third side A first. Okay, so solving for A, we get a squared plus, and if you take a calculator, 18 squared, it's 324. Oops. 324. And 33 squared, 1089. Okay, so a squared would be equal to 1089 minus 324. So it's 765. So a is equal to the square root of 765. Now, I know in the past when we've taken square roots in equations, we often put a plus or minus. Well, that's not needed anymore because does it make any sense that you cannot have a length of a side to be negative? So we don't consider the negative option anymore. So we're just going to go with the positive square root of 765. Now, we need to see if we can break down 765. So if I divide by 5, I get 153. So 765 divided by 5 is 153. And 5, 6, 7, 8, 9. So it should be divisible by 3. It's like 51. So divided by 3 is 51. And 51 is divisible by 3 again. If my memory's correct, that should be 17, but let's check. That is 17. Okay, so we can break this down. Anytime you have a double, goes out front. Okay, and then 5 times 17, 85 will be left inside the radical. So a is 3 square roots of 85. So let's put that up here in the triangle. 3 square roots of 85. Now, once we have the three sides, we can now talk about sine, cosine, and tangent. So the sine of B is going to be the opposite, 18, over the hypotenuse, 33. If you can reduce that, you should. So 18 and 33 are both divisible by 3. So that should give us 6/11. So that would be the sine of angle B. It's the ratio of the sides. Cosine of angle B would be adjacent, 3 square roots of 85 over the hypotenuse, 33. And again, if you can reduce that, you should. Let's go on the page here. So the cosine of B is going to be the square root of 85 over 11. And the last is the tangent. The tangent of B, okay, tangent, let's go back up to the triangle, is opposite. Opposite of B would be 18 over the adjacent, which is 3 square roots of 85. Now, that causes us to have to do a little bit of extra work algebraically. First, we should reduce it if we can. So 18 is divisible by 3, so it should be 6 square roots of 85. Reduce first, and then we want to get the radical off the bottom. So again, from geometry or a previous algebra class, to get a radical off the bottom, we simply multiply by the radical over itself, and we have a square root. So that leaves us with 6 square root of 85 over 85. So that's our final answer. That's the ratio of the sides for tangent. Okay, that's all for that page. Now these three probably do not look familiar. In geometry, you should have been introduced to sine, cosine, and tangent. Here, we have what's called the reciprocal trigonometric functions. Now these are the reciprocals of sine, cosine, and tangent in the order written here. So the cosecant is the reciprocal of sine. That's 1 over the sine of theta. Okay, so if we want to talk about cosecant in terms of sides, okay, we would have to talk about it in the same terms that we talked about sine. Sine was opposite over hypotenuse, so the reciprocal of that would be hypotenuse over opposite. Secant's the reciprocal of cosine. So again, if you remember back, cosine is adjacent over hypotenuse. So this is hypotenuse over adjacent. And then the reciprocal of cotangent is tangent. So it's 1 over the tangent. So if we think about what tangent was opposite over adjacent. So cotangent would be adjacent over opposite. Okay, so we can apply the same thing to that we did with sine, cosine, and tangent to the secant, cosecant, and cotangent. Okay, so let's take a look at this example. This example asks us to find the secant of theta if we know what the cosine of theta is. Okay, so we have a triangle drawn above here with a theta, and we should be able to label these sides as opposite, adjacent, and hypotenuse. Cosine represents two of those sides. Cosine is the adjacent over the hypotenuse. And since cosine is 3 over 4, then we can say the adjacent side is 3, and the hypotenuse is 4. To find the opposite side, we would do the Pythagorean theorem again. So let's say the opposite side we'll call x. So that's x squared plus 3 squared equals 4 squared. So x squared plus 9 equals 16. X squared equals 16 minus 9 would be 7. X equals the square root of 7. Now once you've established that, this side is the square root of 7, and we're looking at theta, you could actually find all of the trig identity or trig functions that we spoke of. We could find sine, we already have cosine, we could find tangent, we can find secant, cosecant, and cotangent. We could actually find all 6 once we establish all the sides. All we're required to find here, though, is secant. So the secant of theta is equal to the reciprocal of the cosine. Reciprocal of cosine, well, cosine was adjacent over hypotenuse, so this should be hypotenuse over adjacent. So the secant of theta is going to be 4 over 3. Now, I know probably some of you are looking at this and saying, wait a minute, why did we just not flip this over to begin with? Why did we have to go through the routine of finding all three sides before we found the secant. Well, you're correct. You could have just flipped over the cosine immediately, but what if it wasn't the secant that was asked for? What if it was one of the other trig functions that was asked for? Well, we would have to find that third side. So it's an excellent routine to get into to find all three sides, because you might not only have to find maybe just one, you may have to find actually all 6 trig functions. Okay, but if you do recognize maybe in the future in a placement exam or something that it's just simply the reciprocal, I agree. Go ahead and just flip it over and be done. It might be something that a test that requires extra time, and I agree with you. I wouldn't waste my time going through all 3 unless I had to. But right now while we're practicing, you definitely want to make sure you do that. And here's exactly why. If you take a look at this example, we're asked to find the values of the 6 trigonometric ratios for angle P. So I'm going to go ahead and circle P, because that is the angle that's going to determine our sides. All right, so the opposite side is 7. The adjacent side is 10. And the hypotenuse is unknown. We can call that little m. So using the Pythagorean theorem, n squared plus p squared equals m squared. 10 squared plus 7 squared equals m squared. 10 squared is 100. 7 squared is 49. So 149 equals m squared. Solving for m, the square root of 149 equals m. Again, we could go through and we can try to divide 149 out, try to break it down to see if it reduces. Again, just a couple of the tricks. Is it an even? Is it end an even number? That would be divisible by 2. That's not the case. Do all 3 numbers add up to something that's divisible by 3? 9 plus 1 plus 4 is 14. Not divisible by 3. It doesn't end in a 5. So this is not looking like it would be something that would reduce. All right, so we're going to leave it as the square root of 149. Okay, so finding the 6 trig, I would start with the 3 basic. Okay, so we'll start with the sine of theta. Remember, sine is opposite over hypotenuse. The opposite side is 7. Sorry, let me fix this. We're not talking about, we could talk about theta, but there is no theta in this problem. If I put theta by p, we could refer to it as theta. But this is actually the sine of angle P. It's very important that you use the correct angle. If you don't label it, no one's going to know what side you're talking about. So the opposite of P is 7, and the hypotenuse is the square root of 149. So as we did earlier, if we multiply by the square root of 149 over square root of 149, hopefully you can start seeing the pattern, and you can just say it's a square root 7 times the square root of 149 over 149. And again, if you wanted to check 149 divided by 7 just to see if it reduces, it doesn't. So it's not a nice number. This is not going to reduce. Whoops, that's different. So there's your answer. For sine, let's talk about cosine. The cosine of P is going to be the adjacent side, the adjacent over the hypotenuse. So that's going to be 10 over the square root of 149. Again, 10 square roots of 149 over 149 to get rid of the radical off the bottom. And the last basic trig function, the tangent of P, that's opposite over adjacent. Go back up to our triangle. The opposite side is 7, and the adjacent side is 10. So this will be 7 over 10. Now, we are asked to find all 6 trig functions. So let's go ahead and find the reciprocals. Now, There's no need to do more work than you have to. So, the reciprocal of sine is cosecant. So the cosecant of p is simply going to be the flip of sine. Now, if we go back up here, let me change colors for this. We have two fractions we could flip. We have the original with the radical on the bottom, and then we have our final answer for sine. If we flip the final answer, that's going to give us a radical on the bottom, which would be 149 over 7 square roots of 149, which is just not pretty. Okay, it's not, we have to now do extra work. Watch this. If we just flip the original, okay, from the sine of p, that would give us the square root of 149 over 7. Okay. Also, we could have just referred to the triangle and just said, okay, well, cosecant's hypotenuse over opposite, so I could just write the hypotenuse over the opposite. That's fine too. Okay, so you can either just reciprocal of the sine or go ahead and use the triangle. Okay, so the next one would be the secant. The secant is the reciprocal of cosine. So again, I'm going to flip the first one, square root of 149 over 10. You can check that with the triangle. Finding the last, cotangent of p. That's reciprocal of tangent. We didn't have a radical involved here, so we just flip over the fraction that we got for tangent, and we get 10 over 7. Okay, so that's how you find all 6 trig functions. Again, without establishing all 3 sides, it is impossible to find the ratio of all 3 trig functions. Okay, last page. And what we have here on the last page is called the special triangles. Okay, again, these triangles should look familiar to you. You should have seen these in geometry. We have a 30, 60, 90 triangle, and we have a 45, 45, 90 triangle. Now, where did these special triangles come from? Basically, the 30, 60, 90 is half of an equilateral triangle. So if we had an equilateral triangle with 2, 2, and 2, in other words, we have 60, 60, and this whole thing would have been 60. We cut that in half, cut it right down the middle. That would give us a 30, 60, 90. So the 30, 60, 90 is half of an equilateral triangle. The 45, 45, 90 comes from taking half of a square. So if you take a square and you cut it by its diagonal from corner to corner, you would create a 45, 45, 90 triangle. Okay. So that's where those come from. Okay. The sides were found. Again, we said one of the sides, for instance, we go back to the equilateral triangle. We said, okay, well, this side's 2. We're making all the sides 2. All right, we cut it down the middle, so now this side over here is 1. So we have 2, we have 1. We use Pythagorean theorem to create the square root of 3. So that's where those 3 came from. Same thing over here. If we had a square with sides of 1, okay, we have 1, we have 1. Then we use Pythagorean theorem to find the diagonal, which would be the square root of 2. Okay, so that's where the sides came from. You really should have these memorized. I guess a nice way to do that, if you wrote down like a ratio, 30, 60, 90, sorry. Okay, so the opposite of 30 is 1, opposite of 60 is the square root of 3, and the opposite of 90 is 2. You need to know that ratio. You need to have that memorized. Same with a 45, 45, strong line, 45, 45, 90. So that's going to be 1, 1, square root of 2. notice that um, uh, there's really no simple way to memorize these. 1 square root of 2. Both 2's show up in the hypotenuse. Maybe that'll help you out. Maybe you can think of some cool way to memorize those. If you do, let me know. But you need to know these. So what we're going to do now is we're going to find the 6 trig functions. Okay. Sine, cosine, tangent, secant, cosecant, cotangent for all of these angles. So you can see we have a chart down here. And we're going to start with 30 degrees. So when we're talking about the sine would be the opposite. So the opposite of 30 would be 1. The adjacent would be square root of 3. And the hypotenuse would be 2. So when we talk about the sine of 30 degrees, that would be the opposite over the hypotenuse, or 1 over 2. At the same time, since we have sine, we could also answer cosecant, because cosecant is a reciprocal of that. So the cosecant of 30 would be 2 over 1, or 2. 2 over 1 is 2, so I'm just going to put 2. The cosine is the adjacent of our hypotenuse, square root of 3 over 2. If we flip that over, that gives us secant. Well, if we flip that over, it becomes 2 over the square root of 3, getting rid of the radical 3. We get 2 square roots of 3 over 3. So 2 square roots of 3 all over 3. And if we look at tangent, we get tangent would be opposite over the adjacent, or 1 over the square root of 3. Getting rid of that radical 3 off the bottom, we got the square root of 3 over 3. And then if we flip that, now look, we could have flipped this original here. Okay, that's going to be the square root of 3 over 1, or just the square root of 3. So we've established all of sine, cosine, tangent, secant, cosecant, cotangent of 30 degrees. All right, so let's do it again. This time we'll do it for, let's go ahead and jump down to 60. We'll stick with the same triangle. So we'll jump over to 60. So the opposite now is the square root of 3. The adjacent is now 1. And the hypotenuse is still 2. So if we talk about the sine of 60, we're talking about the square root of 3 over 2. Opposite over hypotenuse. Again, if we want to do the cosecant right this time, we will flip that over, get 2 over the square root of 3. And if you remember from earlier, that becomes 2 square roots of 3 over 3. So the cosecant, 2 square roots of 3 all over 3. Okay, cosine is the adjacent of our hypotenuse, or 1/2. Flipping that becomes a secant, 2. Tangent, opposite over adjacent, and this one's kind of nice. It's square root of 3 over 1, or the square root of 3. And if we take the square root of 3 over 1, we reciprocate that to get cotangent. That's 1 over the square root of 3. Getting rid of that radical, we get the square root of 3 over 3. Okay, so hopefully what you see here is that all the answers in the 60 are pretty much the same answers that you had in the 30. That's because they both came from the same triangle. All right, let's go ahead and do the 45, and we'll be done for today. 45 is a little bit easier because it doesn't matter which 45 you pick, you're always going to get the opposite to be 1, the adjacent to be 1, the hypotenuse, the square root of 2. So the sine of 45 degrees would be the opposite, 1 over the hypotenuse. That's 1 over the square root of 2. Getting rid of the radical 2, we get the square root of 2 over 2. When we do the cosine, it's adjacent over hypotenuse. Happens to be the same thing. It's 1 over the square root of 2. Getting rid of the radical again. Radical 2, we get square root of 2 all over 2. Tangents, opposite over adjacent, that's 1 over 1 or 1. And then we just have to flip these. Now again, if I refer back to the original of the sign, before we got rid of the radical off the bottom, we had 1 over square root of 2. If I flip that over, I just get the square root of 2. Secant's the same thing, and flipping 1 is 1. Okay, so that would give you the 6 trig functions of 30, 45, and 60 degrees. This ends the lesson for 5.2.